Hey, good morning, everybody. Welcome back. So appreciate you turning in the review yesterday, and so I got the key for you here. So we'll make this together, and I'll need you to check your own work because I wouldn't have time to go back and get those all to you in time for the assessment. So use this key to double check what you did, and hopefully you can do great tomorrow. And let me know if you have some questions after looking at this. So first one is just kind of the basic stuff about vectors and scalars. So important that you remember that vectors include direction. So that's the only difference. A scalar has no direction associated. Vector has direction. So our best examples of vectors, velocity is one we talk about all the time. And the scalar version of that is speed. So that's a good one, just to compare the two of those. Other vectors we have acceleration, direction matters, force, and then displacement is the other one that we've talked about. And then scalars, distance is the scalar version of displacement. Other things like mass, that doesn't have direction associated with it, time. So any of those. So there's other ones for those, but that's a good little list right there. Here for number 2, I just wanted to make sure you're understanding that the size of the vector relates to its magnitude or how much of it. So we've got a 10 Newton to the right and a 40 Newton upward. So easiest I would think would be if you go insert drawing here. And so that's what I was hoping. So if I'm putting an arrow in that's 10 Newtons to the right, let's say I make it this size, then if I'm putting one in that's 40 Newtons upwards, I'd have to make it 4 times bigger than that. So roughly something like this. And I'm just kind of guesstimating at the size, but something like that works perfect for that answer. Then here we've got the riverboat, and I had a couple people ask me about this, so I want you to just be able to make sure. I think some kids got confused with the riverboat thing we did that saw the independence of going across and the effect on time. But here, if your boat is going with the current, so it's like the airplane example we used one day in class here. So if you're going with the current's going with the boat, I would just do 20 plus 5. And then the boat would be moving 25 meters per second. So I'd add those vectors because they're in the same plane. I'd add them that way. If the current is going against the boat, I would do 20 minus 5, and the boat would be going 15 meters per second. And then I put some stuff in earlier so I wouldn't have to take time on the video to do all this, but if the current is perpendicular, sometimes we make the mistake of thinking if it's with the boat, it'll speed it up. If it's against it, it'll slow it down. If it's perpendicular, it won't do anything. And that's not true. Here's where we would use the Pythagorean theorem. So because our resultant is the hypotenuse, we use r instead of c. So we get the square root of a squared plus b squared. And then that becomes the square root of 20 squared plus 5 squared. And so if you punch those into your calculator, you get 20.6 meters per second. So that would be the actual speed of the boat. So it did speed up a little bit because of the current at the perpendicular to it. And then here, free body diagram. So 3 to the right, 3 to the left, or excuse me, 6 to the right and 3 to the left is going to give me a total of 3 to the right. 4 up, 1 down is going to give me 3 up. So again, I've got to use Pythagorean theorem to solve for this. So square root of 3 squared plus 3 squared again, which some people were doing as 6 squared, and that is not the same. So square root of what I would have is 9 plus 9, so square root of 18, which I did some of these earlier, so it's 4.24 newtons. And again, just like always, we want to make sure we're including units in our answer. Now here, just some kind of basic fundamental pieces of knowledge. Force measured in newtons, always. weight is equal to the force of gravity on you. And so then a 5 kilogram object, its weight, if you remember, weight equals mass times acceleration due to gravity. So if I'm plugging that in, that's 5 times 10. And so that would have a weight of 50 newtons. So again, sometimes kids are like, oh, it weighs 5 kilograms, but it doesn't. That's its mass. Is the force of gravity the same on all of us? And that answer is no, because we all weigh differently. So that means that the Earth is pulling on us differently, even though we accelerate the same. Number 9 asks about the horizontal and vertical components of a projectile. And this, I put this in here because when the first day of this unit, we had the demonstration where the ball got shot out horizontally and the one fell straight down. And what I hoped you were realizing at that point was that these are independent of each other. And so that's why the time was the same for those. And that was a really key thing throughout this whole unit. Then best angle to shoot a projectile from if we want to maximize the distance. So that was 45 degrees. And that's just kind of the fact. If you remember that we did the one simulation where we looked at all the angles. So you may want to go back and look at that too if you don't remember. Then projectile shot at an angle. How does the vertical component change over time? It changes by 10 meters per second. So as it goes up, it slows down by that. As it comes down, it speeds up by that. And then the horizontal component, so this stays constant. So if you remember, that's another key piece from this whole unit. So we got some problems here. We had to do some math work for. Ball A dropped straight down, ball B fired horizontally at 5 meters per second. So a key thing here is that the time to do this for both of these would be the same. And so if you knew that and you remembered which formula, which was time is the square root of 2d over a, then you can get the answer, which is the same for both of those. And so that, let me just move down a line here. So that would be the square root of 2 times the distance of 150, so 300 divided by acceleration, which some kids are putting 5 meters per second as the acceleration, and that's the horizontal velocity. So acceleration as this thing falls is 10 meters per second squared. So we just want to plug that in. And so then I'm going to find the square root of 30, and that is 5.47 seconds. And so that's the answer for both A and B. So they take the same amount of time. Vertical velocity after 5 seconds, some people just, I think, rushed through this and they used this time to find it, but it's just after 5 seconds. And so their vertical velocity would be the same for both of them. And to do that, you would do the vertical velocity, and this is when it's falling, equals acceleration times time. It's like instantaneous velocity, if you remember it from back in the beginning. So it starts at a velocity of 0, gains 10 meters per second each second, so 50 meters per second. And then they both have the same. So both of those are that. Horizontal velocity, so ball A was dropped straight down, so its horizontal velocity is 0 meters per second. Versus ball B, the horizontal velocity doesn't change. So if it started at 5 meters per second, it's still 5 meters per second. And then the distance the ball lands from the base of the cliff, well, ball A has no horizontal velocity, so it's going to land 0 meters away. Ball B is, now we're finding the distance horizontally. I forgot to zoom in on this the whole time. I should have done that. I apologize. So now I'm finding the horizontal distance. So this is going to equal the vertical, or excuse me, the velocity in the horizontal plane, the horizontal velocity, times the time. So to do that, that gives me 5 meters per second times the total time, which was 5.47 seconds, and I get for that 27.3 meters. So that's how I would solve number 12 right there. Now we've got the projectile launched, starts with a vertical component of 15, horizontal of 5. So how much time is it going to take to reach its highest point? So its initial vertical is 15, so I would do 15 divided by 10. It's going to change by 10 meters per second each second. So it's going to take 1.5 seconds to get to its highest point. So anytime you have this kind of problem, you take that initial vertical velocity and just divide it by 10. How high is it going to be at its highest point? So here's where I use the distance formula. Distance is 1/2 a times time squared. And so for that, I plug those in. I get half of 10. So 5 times, and I'm using the time to go up. So 1.5 squared. So that's 5 times 1.5 times 1.5, which gives you 11.25 meters. Total time in the air, if it took 1.5 seconds to go up, that means it took 2 times that to total time in the air. So that 2 times 1.5 is 3 seconds. And then to figure out how far horizontally from the starting location it is when it reaches its original height, that just means how far did it go horizontally. So I take the total time by the horizontal velocity, just like I did right up here. So same thing, I can copy and paste this equation. Whoops. And so that's going to give me, again, it was 5 meters per second times 3 seconds. Whoops. And 5 times 3 is 15, so 15 meters away. And how fast was it going when you launched it? So I made this picture earlier, so I'm really finding the resultant here. It was I had this horizontal, this vertical, so I'm talking about the square root of 15 squared plus 5 squared. Oops, did those one? Forgot to take that off. There we go. Let's see. And so square root of 15 squared plus 5 squared gives me 15.8 meters per second. Let's see. So now the ball is in the air, rolls off a table. So a lot of kids ask me about A and B. I'm on a force in the vertical direction. So here's what I need you to know is that this is the downward force. And we talked a lot about the only force on it is the force of gravity. So what would that force be? I'd just have to find the force of gravity on a 3-kilogram ball. So my physics knowledge tells me it's the force of gravity, which equals the weight of that ball. So the weight of that ball is 3 times 10 equals 30 newtons. And then the force in the horizontal direction, so key thing, the velocity stays constant, which means there is no force in the horizontal direction. So not a math one, but a conceptual one, which is why that velocity stays constant. How much time will it take before the ball hits the ground? So formula we used a lot, but some kids seem to be forgetting, is time is the square root of 2d over a. So you just got to have that kind of handy for you when you do the assessment. And then if I'm doing square root of 2d, the table is 2 meters high. So 2 times 2 divided by 10. So I take the square root of 0.4 and I get, where is that? 0.63 seconds. How far from the edge of the table? So again, I'm using the horizontal distance, same equation I've used before. And so my horizontal velocity, it rolls along this table and going this speed, so it's going to maintain that. I don't know why I kept using 5 each time in these examples, but so 5